Hello class. Today we begin lesson number 2 in chapter 9 of polynomials, and this lesson is actually named polynomials. So we're going to enter into this particular subject, and as we have stated in the past, in the previous lesson, that this is so fundamental for the rest of your math life, and so we really need to concentrate on some of this. One of the things I wanted to work with the words first, because even though we're dealing with math, we're using terms. And we saw the term monomial, and now we see the word polynomial. So we might derive mono meaning single, and poly being many. And we can see already that these two words are distinct in the sense that one is referring to singular, the other poly meaning many. But actually a polynomial could actually just be a monomial, and we'll read that in its definition. So why don't we go ahead and begin reading on page 400. And we have a photograph here of these beautiful kittens, and it has it says below, this photograph shows a litter of 13 kittens. The usual number of kittens in a litter is between 5 and 9. Now suppose that a cat had a litter of 5 female kittens, and each kitten later produced a litter of 5 kittens. Okay, so why don't we just go straight to our board here and just take a look at that visually. Okay, we had one kitten, all right, and I'm just going to do that like in a circle. Okay, actually I probably need to be a little closer to the center here. Okay, let's just go here. We have one kitten, or one cat, excuse me, and she had 5 kittens, right? So let's just say 1, 2, 3, 4, 5. Okay, no, this is not an octopus. Just showing you she had 5 kittens, right? Okay, and now the question is, how many would there be together if each kitten later produced a litter of 5 kittens? Now imagine what I'm going to be doing is taking this and applying this to each of these. So I have 1, 2, 3, 4, 5. Okay, and I'm not going to draw these. I don't think I really have enough space to draw it, but just get an idea that of each of these you'll have 5, right? Now, so we have 5 here, and I just kind of use that as one illustration. So we have 5. So what do we have? We have one cat that produced 5 kittens, and then she produced, or those kittens each produced 5, which produced 25 more. Okay, so we have here that an equation, or at least the addition of all these as 1 plus 5, which is here. We have the first cat, second, the group of 5 kittens, plus we have 25 more. And if we add these all together, we would have 31. Now let us consider this problem in the terms of a variable. Suppose that a cat had a litter of X female kittens, and each kitten later produced a litter of X kittens. So remember, X is X, meaning it's the same number. They didn't say X and Y, indicating that there could be 2 different numbers, but they're saying that there was a litter of X female kittens, and that each kitten later produced a litter of X kittens. So that means we're going to change 5 to X, and over here we would have X number of kittens times X, would we not? Because that's really what we had here. We had 5 times 5, right? 5 kittens, and they each had 5, so it was 5 times 5, that was 25. So we now have X representing the first litter, and then each of those having an X number of litter, or litter of kittens. So you would then multiply the same way that we did here. So we have X times X. So that would be the original cat. Let's go back to our text here on page 400 at the very bottom. There would be the original cat, 1, her kittens, X, and the kittens would be X squared. Okay, so we have X times X. That means we have X squared. All right, and again, just note that they're saying that the same number of kittens that or the first cat had X number of kittens, the same number is being produced by each of those. So that's why we're getting the X squared. And it's very important to understand that. So now the expression, we would then write it as such. We would have 1 plus X plus X squared, okay? And what that total is we don't know because it would depend on what X is. So we're not going to make this an equation. This is just an expression over here. And if I said the word equation earlier and I corrected myself, this is really just the sum, okay? Though it is an equation here, but what we're saying here is that we just simply added these. But for us to know what X is going to be, we would have to know how many kittens there are in all, and we could certainly solve it if we knew, but this is just an expression. It's saying that if we have one kitten who produce X number of kittens, and each of those kittens produce X number of kittens, this expression would represent the total number of kittens. Okay? And this expression, 1 plus X squared, is an example of a polynomial. Now let's look at the top of page 401 and let's read. A polynomial is either a monomial or an expression indicating the addition and or subtraction of two or more polynomials. Okay, so it can be just a monomial, but it typically, when we refer to polynomials, we're thinking of many, so we're going to be referring to polynomials typically as more than one. Okay, and and you're also going to learn there's another term. We're going to throw a third term at you, which is called a binomial. And bi, think of that meaning two. Okay, then there would be two monomials. So we're going to use these terms, but again, polynomial can be a monomial. But if we're going to refer to a polynomial that's monomial, we'll generally refer to it as a monomial. But we can say that a monomial and a binomial is a polynomial because the polynomial just represents it all. Okay, so it's the most generic term, let's say, because it doesn't necessarily mean 1, 2, 3, 4, 5. It could be as many as you'd like. Now, monomials are called terms of the polynomial. And note the word term. Okay, we used the word terms before, and we use the word factors. Factors are when we multiply, terms when we're adding and subtracting. So each of these are terms. Okay, so we have three terms right now in this particular expression. The expression 1 plus, and I'm reading back here at the top of page 401, the expression 1 plus X squared is a polynomial because it is the sum of three monomials, and those monomials are 1. Okay, so we have a monomial here. Why is that a monomial? Isn't it supposed to be in the form of ax to the nth power? How can I express that? Well, quite simply, I could simply say 1 times x to the 0 power. 1 to the 0 power is equal to 1. So it'll be 1 times 1, which is equal to 1. So we can say that 1 is a monomial. We also have x. You say, well, how can x be? Well, what is x? Let's slide all the way over here, and we can say x. I don't see a degree. Isn't there supposed to be a degree like n? Well, we can represent anything to the first power. So we have x to the first power would be, and where's the a? Well, we can certainly just substitute 1 as a. So we have 1x to the first power would simply be x. And then lastly, we have x squared. So we have x, so that's the second monomial, and x squared. Again, we already see the degree squared, and we can certainly put a 1 there if we wanted to, and it would be in the form of ax to the nth power. So if we can express something in the form of ax to the nth power, then we can say that it's a monomial. Now, although each term of this polynomial is a different degree, and that's 0. We have 0 in the first one, right? We see that's a 0 degree. 1 in the second, and 2 would be the third. I guess we could have placed that in here somewhere, but we see that we have 3 different degrees, and the degree of the polynomial itself is said to be 2. Now why? Well, let's read the definition. The degree of a polynomial is that of the term having the highest degree. So if we look at these 3 terms, or as many terms as we have, we want to look at the term that has the highest degree, and that would be x squared. And being that x squared, or x to the second power, it's being raised to the second power. The degree would be 2 because it's being raised to the second power. So let's look at some of these examples they give us here. We have x cubed plus 8, a polynomial of 2 terms whose degree is 3. Okay, because we see it's being raised to the third power, and there are only 2 terms here. We also have 2x to the fifth power minus x to the fourth minus 1. And this is a polynomial of 3 terms, so we see 3 terms, whose degree is 5 because we see 2x to the fifth power. Now we have 1/3 x to the seventh power is a polynomial of 1 term whose degree is 7. Very simple. And then -9. -9 is a polynomial of 1 term whose degree is to 0. Very similar to what we had here with 1, where we had 0 was the degree because we would have to represent it in the form of ax to the nth. And the only way we can do that is if the degree here is 0. Okay, because it doesn't matter what x is anymore, because that will always be 1. So we can say that any number, any whole number or constant, or actually any number that we represent can be expressed that number times x to the 0. So we would say it's a term, it's 1 term, and it's a degree of 0. Now it is often useful to write polynomials in one variable so that the term having the highest degree is first. Okay, and this is very important. It's very useful to write polynomials in one variable so that the term having the highest degree is first, the term having the next highest degree is second, and so on. Such a polynomial is said to be written in descending powers of the variable. There are a couple of examples on how this is done, and we'll go over that. What they're basically saying is if I would have taken this expression here that we had, and we had, let's use the example. We have 1 plus x plus x squared. So if we were to write this into, written as descending powers, always remember first off that if there's no negative here, then this is a positive, okay? So always look at these as terms. We have positive 1, positive x, and positive x squared. These are your 3 terms. And they're actually represented not only in the value that they have or variable, but also by the positive or negative next to it. Because when we move these around, we need to carry that positive or negative attribute to the variable or to the number itself. So in this case, as I stated, we have a positive next to the 1 simply because it didn't have a negative. But we can see that we're adding x and we're adding x squared. And the reason we're doing this is because now I have to turn around and move these around. I'm going to shuffle them. But it's so much easier when I envision these as positive and negative terms and not so much as adding and subtracting, because then we might fall into the trap of keeping the positive or negative sign where it is and moving something and changing something from negative to positive or positive to negative. So we're going to move this one all the way over here first because it's the highest degree. We have 0, we have 1, and we have 2. So we'd write x squared. Now I can write positive x squared, but again, we generally don't do that. My second variable, or my second monomial, excuse me, with the next highest degree would be x to the first, and that's positive. So I say plus or positive x. I'm not going to write to the first. We know it's there. And then my last one would be positive 1. So again, notice how I move this around. Now my only example here, you have to be very careful. I'm going to show you what would have been, let's say this would have been minus. I'm going to use this as an example, class. Let's say that's minus. All right, I would have had to have written this as negative x squared plus x plus 1, okay? And again, let's not fall into the trap, because the trap might have been to have moved these variables around, rewriting this, and we learned this earlier, and say, well, it's positive in the beginning, and plus x, and then subtract 1. All right, and that would have been wrong, because we're saying that 1 is negative, and we're saying that this is and we're adding this, so that would have been wrong. Okay, so just wanted to use that as an example. So if we were rewriting this in descending powers of the variable, we would say x squared plus x plus 1. Okay, now let's take a look at the examples that we have here, and we'll just let me see if I can just go ahead and paste my board back on here and get my pen back. We have rewrite the polynomial. Let's put it on the board here. 6x, oops, minus 3x squared. Okay, I see something going on here. And minus 1 and plus x cubed. Now, again, if we state this particular expression, we're going to say plus and minus all the way through. But again, I will state you need to view these as positive and negative terms. Okay, here, what do we have? We have positive 6x. Over here, we have negative 3x squared. Over here, we have negative 1. And over here, we have positive x cubed. Okay, and if we do this, you don't necessarily have to put blocks around them, but you should identify them, and if it helps you in the beginning, go ahead and do it. You can just do it on your paper so you can see it clearly. As you write algebra and you see it in front of you, it's sort of like looking in a mirror, okay? And it's just constantly it's teaching you what you're writing. In other words, it's going to show you the values as you move them around, how you're moving, and your eye just becomes that much keener towards math, and it's going to be very helpful later on as these problems become much more complicated, particularly as you go into Algebra 2 and you're going to have a higher degree of complexity of these expressions. So it's very good, plus the fact that when you get into factoring, factoring is a challenge, and again, you sort of develop a keen eye to the factors, okay? And factoring, for instance, if I see 64 right now, what would I see? Well, I see factors of 1 times 64. I see 2 times 32. Again, my eyes have seen this. Why? Because I have seen this over and over. I have visually have seen this. 4 times 16, because I've done a lot of homework over my life. Well, at least when I was in high school and I learned algebra, but I just did all my homework, and actually this goes back way before algebra even. And I'm sure this is just more like a grammar school learning math, and just doing that math over and over made me that much keener towards figuring out seeing all of these numbers when I just see one number. So the same thing's going to happen when you see these polynomials. You're going to start catching things, particularly when you start identifying the forms and say, oh, okay, this looks pretty complicated, but it's not as complicated as it looks. I can start factoring here, and I can reduce these terms, and I can make it simpler. So let's take a look. How are we going to do this? Let's read. The degrees of the terms of the polynomial 6x minus 3x squared minus 1 plus x cubed are 1, 2, 0, and 3. So we have 1 here. That's the degree. 2 is the degree here, 0 is the degree here, and 3 is here. So what do we have to do? Well, we have to write them in descending order. We have to put them in order descending. So we would start with the 3, and let's grab this entire term here and just place x cubed. I mean, I could put plus here if I wanted to, but again, it's the first one, and if it were negative, I'd definitely have to do it, but the positive is already implied. So that one's already done. I need number 2. What's number 2? I have negative 3x squared. Notice I didn't say minus 3x squared. I'm using the word negative now because I'm moving terms around. My next one is 1, positive 6x. So that one's done. And my next one, 0, is a negative 1. Okay? So we don't have to worry about what we're adding and subtracting. We're just moving these terms around, and we're just being very careful with our positives and negatives, not our adding or subtracting. It's positives and negatives from here on forward. Okay, this is very important that you learn how to view terms this way. Make it so much easier later on when you do have these much more complex problems. So, in doing this, we have rewritten this, and we see that written in descending powers of x. Now we can say, well, it's x cubed minus 3x squared plus 6x minus 1, and this has a degree of 3. Okay, the degree of this polynomial is 3. Why? Because it is the highest exponent here. It's 3. So we we can move on to example number 2, and we have simplify the polynomial. And let's go ahead and write this. I'm going to probably need a little bit of room here. So why don't I just go ahead and paste my new board back on here, get my pencil back, and simplify 10x plus 4x to the fourth. Okay, my x's are just not coming out well today, are they? 4x to the fourth, and we have minus 2x. And again, I'm reading this as the expression. I will eventually start speaking in terms of positive and negative terms, but for the meantime, I have minus x squared, and then I have plus x to the fourth. Okay, so by combining terms of the same degree, okay, we can change these around, we can look at them, and it's going to help us to simplify this problem. It looks longer, it looks big, but we can identify some of these terms. And we can see that these terms are, as they show, there's the 10x and the negative 2x. Okay, now you see that I'm going to start breaking this apart. I'm sorry, let me make that square a little bit better. So it's really more like a trapezoid, I guess, when you get into geometry. But let's just put a box around this. So that's positive 10x. I have positive 4x to the fourth. I have a negative 2x. I have a negative x to the fourth power. And I have a positive 4x to the fourth power, okay? So we identified we have 5 terms. Some are positive, some are negative, some have variables. Actually, I believe they all have variables, but they have varying degrees. So let's take a look which degrees. Remember, we can add these if they have the same degree and the same base. Okay, that's something that we've already stated. So, and in our first lesson. So let's take a look. We have 10x and negative 2x. And you can see where they combine these two, okay, and they get 8x out of these two, right? So we have positive 10x and negative 2. You should be able to do this very quickly in your head. You've had a lot of practice with this. Now we also have a positive 4x. Oops, I went too far there. We have a positive 4x to the fourth, and we have just 1x to the fourth, or x to the fourth, and that would give me a 5x to the fourth power, right? So we've eliminated this, and we've eliminated this, and we've eliminated this, and we've eliminated this. So now we're left really with just three terms. We have 8x, we have 5x to the fourth, and we still have the negative x squared, simply because we weren't able to combine that with anything. So with these 3 terms, we need to now put them, well, we could write them as the book shows. We could say we have 8x, okay, and we have plus or positive. Again, I probably could have written this as a positive over here. Maybe it make it a little easier to identify later. And this is a positive. So we have 8x, we have positive 5x to the fourth, and we have a negative x squared. Okay, so we have 3 terms. I'm going to block these out again because we need to put them into descending powers. So put my blocks around it. I'm identifying their positive or negative. Call that like an attribute to the actual. It's probably more of my computer thinking when I think of things having attributes. But you know, things can either be positive or negative. So in this case, we're going to put these in order, and we're going to say that we have 5x to the fourth, or positive 5x to the fourth. And then I'm sorry, that was our first because it was the fourth, it was the highest. Our next highest is the 2, so we'll put negative x squared. And our last is positive 8x. Okay, now we have this expression, 5x to the fourth minus x squared plus 8x. And again, this is a polynomial, okay, which is, and they don't ask to, well, they don't state it, we weren't asked, but what degree is this polynomial? Okay, we had that in the previous one. We said it was the polynomial had a degree of 3. This one has a degree of 4, okay? But they don't ask that in this particular example. So that is the end of lesson number 2, and be very thorough with your homework and pay close attention to all these details. Also, try to be as neat as possible with your work. It's going to be very helpful because you're going to move things around. And when you're doing your work, don't do this in your head. Try not to do this all in your head, because it generally will lead to mistakes. And once you have one mistake, it's going to simply cascade into an error for your final answer. And so be very neat. Try to be neat. Sometimes we're not as neat as we would like to be, but spend time with it and work slowly with it. And this is going to help you, particularly as you're looking at what you're writing. And the answers are going to be contained within. It's just a matter of solving, using all the information that you've been given.